Here at SDT, we've got a really simple view for inspecting steam traps with ultrasound. People do have a tendency to overcomplicate the issues. In our simple view of life, a steam trap is nothing more than a valve with an IQ of 1. It knows just enough to keep the steam inside of the system and to dump the condensate and bad gases out of the system. Besides that, it's basically just a valve. Now, there's many different types of steam traps, and each one of them are designed to work with specific processes. Some are considered float-type traps. They work on a similar principle as your toilet. Like when the float is down, because the water reservoir is empty, and as the float rises up, as the water reservoir fills, it reaches a certain point and it closes the valve to stop the water flow. In a float steam trap, the float moves as condensate and contaminants collect in the reservoir, and then when there's enough condensate accumulated, then the float triggers the valve to open up and purge, and that keeps your steam system pure. Another type of steam trap is known as a thermodynamic type. Now, thermodynamic traps work on the principle of differential temperature between pure steam and condensate. They have a little metal disc, and that disc moves as condensate collects and the disc cools down. And when the disc reaches an engineered temperature, it moves just enough for a valve to open up and then purge the trap. When steam comes back in, it heats the disc back up, and then that closes the valve again. So you can see there's different ways of opening and closing the valve, but they're basically all doing the same thing, opening and closing to get rid of condensate and gases. It's kind of strange. A lot of people confuse steam and condensate. Steam is an invisible gas. That's right, steam's invisible. If you can see it, then it's not steam anymore. It's condensate. The thing about steam is it takes a lot of energy to turn water into steam. The last time I checked, energy costs money. So steam, like any other process gas you may use, has to be considered a resource. Steam is a paid-for asset, and as such, it's an investment that needs to be protected. Let me give you an example. Let's take 1 pound of water at room temperature, 70 degrees Fahrenheit, and let's add 142 BTUs of heat energy to that 1 pound of 70-degree water. Now I'm going to have 1 pound of water, but by adding that heat energy, I've brought it up to 212 degrees Fahrenheit, or 100 degrees C, the boiling point of water. But it's still not steam. It's just really, really, really hot water. To turn that 1 pound of water at the boiling point into steam, I now need to add an additional 970 BTUs of energy. And then I can turn that 1 pound of boiling water into actual steam. Now, if I've expended the energy to convert room temperature water to steam, I want to do everything in my power to keep that steam, to keep it steam. Enter the steam trap, these low IQ valves. They play an important role in keeping steam systems free of water and contaminants. Properly working steam traps protect our investment in steam. So, how can we be sure our steam traps are up to the task? So the consensus method for testing steam traps is to use 3 senses. We're going to look, we're going to listen, and we're going to feel. Visual inspections, they can alert us to things that don't appear right. For example, if you see water pooling on the ground or condensate vapor shooting into the air, those can indicate some kind of an external leak. Listening with a quality ultrasound instrument gives us an idea of what's happening inside the steam trap. And while we're going to insist that you never actually place your bare hand on a steam trap to feel it, taking its temperature with a non-contact spot radiometer is a great way to confirm your ultrasonic inspection, and even to confirm that the steam trap's working in the first place. So ultrasound equipment offers a static decibel measurement from the steam trap with the signal heterodyne so that you can hear the converted ultrasound signal in the headphones. This allows inspection of steam traps in high noise environments, and it lets you actually listen to what's going on inside the steam trap. Advancements in ultrasound detectors by SDT include a spot radiometer for temperature measurements, as well as dynamic signal recording. So we're taking those visual and touch senses and we're enhancing them. If a static measurement is a single point in time, like a photograph, a dynamic signal should be considered like a digital movie. So dynamic signals allow inspectors to actually visualize the steam trap as it cycles from an open to a closed state. You'll even see some peakiness sometimes in a time waveform that could indicate a leak, or could indicate bypass, and sometimes it's just indicating steam or condensate flashing back into steam because of a drop in pressure. An increase in pressure. Look at the dynamic time signal of a steam trap that's functioning properly. Here you can see it. It's opening here, it's purging, it's closing, it opens again, and then it's purging again. Very simple. A valve with an IQ of 1. Now, look at the dynamic time signal of a steam trap that's not working well. In this visualization, you can see the trap is continuously closing and purging, but the cycle time is way too short. So this trap's functioning poorly, and it could be for any combination of reasons. For instance, the steam trap could be undersized for the application. Well, that's an engineering problem, or is it? I mean, there could be other steam traps in the system that have failed. So because those other steam traps have failed, now this steam trap is working double time to take care of the ones that have failed. So that's causing this steam trap to be overloaded. So now it's undersized. There could just be a mechanical fault with the trap too. Either way, it's not doing its job properly, it's not efficient, it's not economical, and it's not protecting your investment in steam. Here's a dynamic signal of a good steam trap. It's doing exactly what I expect from a steam trap. It's collecting the condensate. It's open when it's time to purge the condensate and bad gases. It purges here, and then it closes again so that the cycle can repeat itself. Again, simple. A valve with an IQ of 1. How about a dynamic signal taken on a steam trap that has failed closed? Look at the y-axis scale. There's not really a lot of signal here. The temperature is cold, so the trap has failed closed, or there's a blockage somewhere. Compare that with a trap that's failed open. It looks real similar, just a sea of blue noise, but look at the y-axis. It's showing much higher signal. So that's indicating that it's wide open and that there's a lot of turbulent flow across the valve. This is what most inspectors want to find. They want to find steam traps that are throwing good money steam directly into their condensate system so that they can get those steam traps identified, replaced, and restore their entire steam system to the efficiency that it was originally designed for. Many steam system inspectors rely on temperature only to determine if a steam trap has a problem, but sometimes this can be misleading. To determine if a trap is working at all, we want to determine if steam is getting to the trap, or if there's a blockage somewhere. If the trap is closed and plugged water can build up in the system, the trap won't be as hot as it should be. I've never been near a steam system and not been able to find a pressure gauge. And since I know there's a consistent relationship between temperature and pressure, it's relatively easy to estimate the expected temperature of a trap if you know the pressure. For example, a steam trap under 5 bars of pressure, it's going to have a temperature of around 250 degrees Fahrenheit. As a rule of thumb, there's a heat loss of 10% across the pipe. If the steam system is 5 bars, it should be around 250 degrees Fahrenheit, less about 10% for heat loss. So using my SDT 270 in the temperature mode, I would expect to measure 225 degrees Fahrenheit on the outside of the trap. If it's lower than 225, then I know there's either a problem or that part of the steam system is not in service. Conversely, if the trap is hotter than I expect, then I'm going to go downstream side of the trap and listen with contact ultrasound. I expect to hear nothing. If it's hot at the trap and quiet downstream, then likely the trap is working just fine. But you can't rely on temperature alone. Sure, taking a temperature measurement downstream and upstream, we should expect some differential, and this will be the case most of the time, but there could be back pressure existing in the system. Here's an example from an ultrasound inspector at a New York City hospital. So He was following the correct procedure. He compared the upstream temperature to the downstream temperature, and he discovered that the downstream side was hotter. This is the opposite of what he expected, and it's also the opposite of what we trained him to expect. The upstream side of the trap was 110 degrees Celsius, and excuse me for switching from Fahrenheit to centigrade, but this is the example we've got. And the static ultrasound measurement recorded 5 decibels of ultrasound. We're on the upstream side. The downstream was much hotter and louder with a measurement of 15 decibels. So we tried to decode the problem, and we took additional temperature and ultrasound measurements going further downstream from the trap. Sort of like the ABC method. So A being the first measurement upstream, B being the first measurement downstream, and then C being additional measurements taken further and further and further downstream of the trap. The further we went, the louder it became ultrasonically, and the temperature was hotter too. So the trend continued until we reached a header. That's when we discovered that there were actually 2 steam systems. One was a high-pressure system, and one was a low-pressure system. So 2 different pressure systems, 2 different temperature systems, and both of them were dumping into a common condensate removal system. So from the higher pressure system, there was a steam trap failed open and dumping live steam into the common condensate system. The steam and the turbulence was in close proximity to the first trap that we tested. And that explained both the increase in temperature at that trap, and it also explained the ultrasound being louder on the downstream side of the trap. This high-pressure failed trap was feeding live steam and ultrasonic turbulence directly into the condensate removal system. So if you've never tested a steam trap before, or you're just getting into testing steam traps and you're not exactly sure where to begin, SDT's put together a steam trap decision tree. And here's what it looks like. And it looks like a lot if you look at it all at once, but if you break it up into the tiny bits that make it up, then it actually has a rather logical workflow to it. And here's how you would use it to determine the condition of a steam trap. The first thing you need to do is establish if the trap is working or not. And that means, is it online? So start by finding out the operating pressure of the steam system. And since there's a direct correlation to pressure and temperature, knowing the pressure makes it easy to estimate what the expected temperature of the steam trap should be. Remember to subtract the 10% to compensate for heat loss across the piping. So if the temperature is lower than you expected, then confirm that the trap is in service. Maybe it's not even in service. And if it's not in service for whatever reason, then you're done. I mean, you can't evaluate faults on a steam trap if it's not in service. So on to the next. If the temperature is too low and the trap is in service, then listen to it and measure its ultrasound signal. If the signal is low and constant, the trap is either failed in a closed position or there's a blockage up or downstream. If the ultrasound signal is irregular, take a recording of its dynamic signal and then view it in the time domain. Also record the upstream temperature. At this point, it may be useful also to compare data with a known good steam trap to build a reliable diagnosis and get some baseline data. If the temperature is normal, then listen to the ultrasound signal. As we discussed earlier, a good steam trap will have distinct opening, closing cycles, and these cycles should be spaced apart anywhere from 10 to 60 seconds, depending on the process, depending on the system. If the cycles are normal, confirm the downstream temperature is lower than the upstream temperature and conclude that the trap is working. Should the cycles be questionable or non-existent, identify if there's a distinct rushing sound and if the downstream ultrasound signal is high. If yes, the likely diagnosis is a large passing leak from the trap being failed in the open position. If not, record a dynamic signal and display it in the time domain. Record the upstream temperature and perform diagnosis, and then determine early failure mode or good condition. Look, there's tremendous opportunities for energy savings from a diligent steam trap survey program. but we need to treat steam as we would any other process gas. Steam represents an investment in energy. A properly engineered steam system should have sufficient condensate removal apparatus in place to protect that investment. As these apparatus age, they lose their efficiency and their ability to keep steam pure. Remaining vigilant requires routine surveys with a quality ultrasound device such as the SDT 270 Steam Surveyor's Kit and a qualified and trained inspector. Stop wasting steam and adversely affecting your product quality and renew your steam system's efficiency. The first step is to implement an ultrasound testing program today. I want to thank you for your attention. The final slide in this presentation is going to show you some contact information for SDT. Here you can find our phone number, you can find an email address to contact us, or you can visit our website where you'll find other information on training, information on other applications and solutions that you can do with ultrasound. So thank you, and let's hear more together real soon.